So the inclined plane. Obviously, you guys would refer to the inclined plane as the ramp. Okay? Why do we have ramps? Why? Because they're useful. Yeah, it makes it what? Easier. Okay? How is a person on a wheelchair supposed to hop up 5 meters if there's no ramp? Right? Okay? So also what the ramp does is it takes the gravitational force and it multiplies it by a factor that's less than 1. So the gravitational force is what do you call it? It's almost like restricted. It's lowered. So draw yourself an inclined plane. All it is a right-angled triangle. So make it big. And let's put the 90-degree on the right side. And what you're going to do is you're going to draw our standard sort of box, sort of like this. You know how we've been doing the boxes for the free body diagram? Okay. And if you are neat and tidy, these notes will look nicer than if you're sloppy. So please put in some effort with your ruler. Now, imagine you were to just drop an object versus if you were to drop the object on the ramp and then let the object slide down the ramp. Which force is going to have more magnitude? The object falling down the ramp, or if you just drop it? The ramp like slows it down, right? Right. So what happens is the force due to gravity on the box is the same, obviously. The force of gravity still points down. However, what the ramp does is it puts it at an angle. It puts the gravitational force almost at an angle. So what we're going to do, you'll always be given usually the angle of the ramp. Now what we're going to do is we're going to break Fg, this downward pointing force, into its components. So Fg will have two components. What are they? Sort of, but it's going to be at an angle, and we're going to give them new names. So you know how we had broken things down into their x and y component? Well, this Fg is all y, right? So we're going to break it down into something else called parallel and perpendicular. Okay? So what's going to happen is we're going to make a right-angled triangle. And we're going to break the force due to gravity into two components. And one of them is going to be called force parallel, and one of them is going to be called force perpendicular. Now, which one of those do you suppose is going to be the force perpendicular? The longer one or the shorter one? The longer one. Why? Because it's perpendicular to the surface of the ramp. F, that's a symbol for parallel, or pardon me, perpendicular, like this. It makes a 90. You guys know what perpendicular means? 90 degrees. Okay? And we're going to call this one down here F parallel. So those are the two symbols for parallel and perpendicular. Okay, so what ends up happening through some very basic mathematics is that the angle made in here is the exact same angle as theta. And if you wanted me to show you how that is true, I can definitely show it to you. But if you want to just take it for granted, that's cool too. So this angle in here is the same as this angle in there. You want me to show it to you? Okay. So let me just adjust this so it looks better. Say that again. How far to go? What do you mean? Oh, the force lines? I guess you can just do it from, it should be like the middle center of the box. Like right on the ramp. Okay, so you want me to prove it to you? Okay. So call this O, call this C, and call this E. These are points. O, C, E. Okay, so then we can do theta plus angle OCE is equal to 90 degrees. And that's just from the interior angle sum of a triangle, 90. So this angle and this angle and this angle make 180. So take away that angle. Like all three angles in a triangle add up to 180, right? And this angle down in here is 90, right here. So take that one out, and this one add up to 90. Do you agree? Okay. The other thing is if you examine in here, you also see a right angle. So you could write that one down as well. So angle OCE plus alpha is also 90. Do you guys see that? Because this is 90. So OCE and theta also add up to 90. Do you guys see that? Yeah. And then you would just subtract. Those go away, and you have theta minus alpha is 0, which means they're the same. So subtract theta minus alpha equals 0. Whoops. Equals 0. So therefore theta equals alpha. And then once you just accept that, then you can start working on this. The other thing that you'd want to get out of this is formulas for F parallel and formulas for F theta. And since we know that theta and alpha are the same, you can just use theta, which is the angle of the ramp. So it's really quite nice. Once you just admit that theta is the same as alpha, and I think 9 times out of 10 you're given alpha or you're given theta, so you just use it. So it's really straightforward in that sense. And then how do we get formulas for theta and, or pardon me, for parallel and perpendicular? Good. Sine and cos, obviously, good. Because FG is our hypotenuse. You guys see that? So how would we find a formula for F perpendicular using alpha, which is in a sense theta? So right here, perpendicular, is it the adjacent or the opposite to F perpendicular is adjacent to alpha. So for F perpendicular, you're going to use FG cos theta. And therefore for parallel, because it's the opposite of alpha, you're going to use FG sine theta. Now how can we relate FG cos theta and FG sine theta, F perp and F parallel, to stuff we're already familiar with? So like if we look at this box on the ramp, what other force are involved? Fn, good. Which way does that point, Chris? No. Normal forces are always what to the surface? Good. So it goes like this. So I guess if you were to draw it properly, it would be the same line as this is F normal. F normal is always perpendicular to the surface. So if I lean on this door, the normal force is pointing away from the door, perpendicular to the door. If I'm standing on the ground, it's pointing up from the ground, pointing right from this door, right? F normal. Okay. So because this surface is at an angle, the normal force is at a right angle to the surface. So you can jot that in. And normal, i.e. perpendicular to surface. So right away you can start to see the equal opposite in the Newton's force laws. What's the equal opposite for F normal? Well, it's F perp. F perp I always call it. Instead of F perpendicular, F perp. You guys okay with that? Okay. Now what also happens? What if there was friction? Well, obviously, if this box is sliding down this ramp, what would try to stop that downward movement? Friction. And which way does the friction go? It always opposes the motion. So if a box is sliding down due to its weight, gravity's making this go down the ramp, which you're used to, what's trying to stop it is friction, and which way does that point? Okay, so here we have force of friction. And if you're trying to analyze force of friction, what are you going to have to compare it to? Force, not perpendicular, but parallel. So I'll highlight those for you to show you that it's the same force vector. This and this, same force vector. It's just sort of like picked up and transplanted over. So those are your parallel vectors. So in order for this box to slide down the ramp at a constant velocity, what would have to happen? Which ones? Be specific there, Mr. Hamza. Not necessarily horizontals. The parallels, yeah. So in order for this box to slide down the ramp at a constant velocity, the parallel component of the weight force has to equal the force of friction. So everything that we've been doing with the horizontal, you now just get a little tilt. Your head just has a little tilt on it. Does that make sense? Okay, and then if we're talking about normal force, you're going to have to use the perpendicular component of the weight. Okay, let's just back up a little bit. Why does this box fall down the ramp? Gravity. And which way does gravity point? Down. So that's where we begin. And then we break the gravitational force into parallel and perpendicular components at a right angle so that we can analyze what's happening on the tilt. Okay? The normal force goes with the perp. The frictional force goes with the parallel. And those are your formulas for perpendicular and parallel, always. Moreover, not on your formula sheet. Question? Lean on the door? Straight right. Normal force straight up. If I lean on this, so I'm applying a force, like, how is that better? Oh yeah, there's normal force on my feet too, yeah. And there's normal force on the door too. I don't know. Maybe we could talk about that after, me and you. Okay. Okay, so let's jump into the workbook. Because to be honest, I just want to focus on the ramp here. Page 127. All right. So the book also has some summary notes for you. And you can see very similar notes. Okay. The first question that they offer is example 1, and you can see what's happening here. Their free body diagram on the ramp. Okay. What page? 128. So a 275 Newton box, what does that mean? Good, that's the what of the box? The weight of the box. Could you find the mass of that box? How? Good, that's done here. Okay. Look at the F net formula. I know some of you are hesitant to do that. So what is this F net? This would be like F net for the parallel. Oh, that's too dark. Parallel component. This would be F net parallel. That's like the F net for this, for the ramp. F net parallel. And for these ramp questions, you would only ever have to worry about F net parallel because the F net perpendicular is balanced. These are balanced. Right? It's not accelerating like at an angle into the air or through the ramp. It's all about sliding up and down the ramp. So we're only worried about the net force on this tilted dimension, if you will. All this is like a one-dimensional problem at a tilt. Does that make sense? This is no different than me pushing a crate on a flat surface, except now we're at a tilt. And the driving force is weight. Like, what's the driver of it? Remember the pulley? A mass on either. What was the driving force? Weight. The larger weight, that was the side it went. Same with the ramp. The driving force is the weight. And in this case, what's the force trying to stop that? The friction. Okay, so you can see that in their F net formula, you have the driving force, which is the parallel component of the weight, minus the friction of the surface. Okay, and they go and find F parallel using some basic trig. And again, you can literally memorize this. You can memorize that. Okay, or you draw the picture. And then they went and found the acceleration as well over here, which looks like the net force divided by the mass, which you should be familiar with at this point. Net force divided by mass gives you acceleration. Okay, so with the problems, they're going to be giving you appendix questions with free body diagrams. That's going to be part of your homework. Okay, and because of the appendix there, I'm going to leave that as exercise. And then let's do a couple questions together. So I get you started on your homework, and then I'll let you be. So with questions 4, 5, 6, 7, 8, 9, 10, 11, there's 11 questions. How many do you want me to do? All of them. Do 11? Want me to do 11? How about we do the first one? The 4 is too easy, I think. I think 4 is too easy because there's number 4 just wants you to find the components, so that's too easy. And then number 5 is frictionless. And then number 6. I think 7 is where we should go. Okay, 7. Okay, a 60 kilogram skier is traveling at a constant velocity. Please highlight that. And then as soon as you see constant velocity, what's the... Good. Constant velocity, acceleration 0, and therefore F net equals 0. Okay, that is a must know. You have to be able to do that. Okay, so the skier is going down the... This is just garbage. Okay, so skier's going down a hill. The slope is 38 degrees. Determine the skier's coefficient due to friction. Okay, so let's draw the ramp. or the ski hill. It's just a ramp. Please try your best to keep these like straight, right angled. It'll really make your diagrams much easier to read. Okay, so 38 degrees in the corner, and then you just put Johnny Skier here like this. And it's 60 kilos. Okay, where do you start on these FBD diagrams on the ramps? Start with your force of gravity. Draw straight down. Start there always. Straight down, and I just go from the middle. I just go from like the middle of the ramp and the box at the bottom there. So then you can break that FG into its two components. You have the perpendicular, you have the parallel. Right angle right there. This is F parallel. This is F perpendicular. Any questions on that setup? Josh, you just working ahead, or like what's the story? Why don't you just work with me? I'm almost done. I'm just going to do one, then let you guys work. Okay, so let's establish some values. FG, 60 times 9.81. $588.6. F parallel. F parallel is opposite to our 38 degrees. Remember, you also have 38 degrees up in here. So to get F parallel, which is the opposite side, you're going to use sine 38 times FG. So I'll just take that 588.6 and times it by sine 38. Okay, I got 362.4. And of course these are newtons. And we have F perpendicular, which is the adjacent, so the cosine. So you have cosine 38 times that 588. So I'm looking at like 463.8 Newton. So that's a great place to start, especially if you're maybe stuck. Okay, so now jump into F net. And again, what is this F net going to be for? This is which component is F net? It's this. This is what we're interested in. It's the F net of the ramp. That's what we care about. Have you already done this question, Josh? Or no? Okay. Okay, so F net on that angle. So let's take a look at what forces are acting on this box. So obviously there's a normal force, and it should be, that's not doing it justice. I drew it so big. Okay, so there's Fn. It's got to be the same size as F perp, because they're balanced. Now, think about this. What makes a skier go down the hill? Gravity. But you would experience the full force of gravity if you were in free fall. Is the skier in free fall? There's a ramp. So you only experience a portion of the gravity based on this angle. And what happens when you multiply by like sine theta, when theta is between 0 and 90? you always get less. So you're only experiencing a portion of this gravitational force, and you're experiencing F parallel. So you can sketch in F parallel. This is what's making you go down the hill, F parallel. What's stopping you from going down? Force of friction. What size do we draw the force of friction? Equal. Why? Constant velocity. Good. I'm not sure where that purple highlight just went. Just disappeared on me. That's weird. Put that back. Okay. So what are all the forces involved on this purple angle, purple slope? Yeah, I would just put force parallel first because it's like the driving force, and then the one that's trying to stop it is the force of friction. And you got the driver and the stopper. Okay, and we know from above, constant velocity F net is 0. And some of you that are quite bright at physics, you could have skipped these 2 steps and just went to here right away. That's what Mr. McCracken was doing with you guys the other day. He kind of just like went right to it, you know what I mean? So, if you're quite bright, you can just jump into this, but I do recommend that you go through the process. Hamza, be kind. Okay, so FF is F parallel, so FF is this 362.4 newtons. That's from over here. And they want the coefficient of friction. Coefficient of friction, that formula, force friction, this is right from the formula sheet, mu Fn. Divide out Fn, very nice. Okay, so what's the force of friction? 362.4 newtons divided by now Fn. Well, what's Fn? Good. This Fn is going to be balanced by F perp. So we sub in there F perp, which is 463.8. You can see the newtons will cancel, and you get this coefficient mu, which is unitless, 0.78. Okay, so when you're doing your homework, you're going to see some various things thrown at you. Like on 8, they're giving you the acceleration, so there's going to be a different approach than 7. Every question might have a different approach, but you have to use these same principles where if you want to talk about force friction, you got to talk about force parallel. If you want to talk about force normal, you got to talk about force perp. Okay? So let's do some work for 20 or 30 minutes, and then maybe I'll bring you guys back up to the front here for some more questions. So I'll let you guys get to it, pencil and paper. I'll pause the